So in this exercise, we're going to use a dimensional analysis for a slightly more difficult problem. We will find out the resistive force, or the so-called drag force, acting on an object which is moving in the air. So let's say that we have an object of an arbitrary shape which is moving in air with a certain speed. So the question is, what is the force, the resistive force acting on that object? Now, to work out the force, we first need to think about the different physical parameters that the force could depend on. So let's think about what are the different parameters that the force can depend on. Well, first of all, the force should depend on the density of the air. Now, the denser the air, the more difficult it is for the object to go through it. For example, in a vacuum, there is no resistive force, and so the dependence on the density of the air is clear. So then, what else? It should depend on the area. The greater the area, the more difficult it is for the object to go through the medium. Like think about the parachute, for example. So it should depend on the area. And we should say the leading area, the area which is facing the resistance. What else? Well, it should depend on the velocity of the object. The faster it moves, the more is the number of molecules of the air that it collides with per unit time. So it has to depend on the velocity of the object. Now, pause for a second and think if there are any other physical parameters that the force could depend on. Another parameter that it could depend on is the geometrical shape of the object. Now, you can have the same area but different geometrical shapes. So it has to depend somehow on the geometrical shape of the object. Now, however, there is no simple parameter that we can use to quantify this dependence on the geometry of the object. And therefore, this geometrical shape of the object will eventually be part of this multiplication constant that we have in front of the equation. So let's leave it there. So now these are the three parameters, the independent parameters that influence the resistive force or the drag force. So to start with, we need to write down the dimensions of all the variables. So let's start with area. So dimensions of area are L squared. Then we have density, rho, that's mass per unit volume. So m over L cubed. Velocity, v, that's length per time. And then finally the force. Now recall what were the units of force. Units of force, F, were kilogram, meter per second squared. So the dimensions would be mass, length, T2 minus 2. So the next step is to make an assumption regarding the functional form of the equation. So we will say that the force is equal to some multiplication constant k times a to power alpha, rho to power beta, v to power gamma. So now the next step is to say that if the equation that we assume is correct, then it has to be homogeneous, and the two sides of the equation should have the same dimensions. So on this side, we have m, L, T2 minus 2. K has no dimensions. A is L squared, so that's L2 alpha. Rho to power beta, that's m beta, L2 minus 3 beta. V to power gamma, that's L gamma, T2 minus gamma. So now let's compare the two sides. So here we have m, and here we have m. So which means that beta is equal to 1. Then here we have L, here, here, and here. So you can say that beta, 2 alpha plus beta, 2 alpha plus minus 3 beta plus gamma, right? So 2 alpha minus 3 beta plus gamma equals 1. And then finally here, T and T. So gamma is equal to 2. So we know beta, we know gamma, and from this equation we can calculate for alpha. So alpha is equal to 1 minus gamma plus 3 beta over 2. So 1 minus gamma, that's minus 2, plus 3 beta, that's plus 3 over 2, and that gives you, So now we have all the variables, alpha, beta, and gamma. So we can now write down the final expression for the force. So K, A to power alpha, so that's just A, rho to power beta, that's just rho, times V to power gamma, that's V squared. So now we got to this final form of the drag force. As you can see, it depends as a square on the velocity. And it turns out if you actually perform an experiment for high speeds, this turns out to be true. Indeed, the force depends as a square on the velocity. And as you can see in this example, we haven't started from any physical parameter, from any physical laws or some basic principles. We just started with the dimension analysis, and we still managed to get the functional dependence of force. If you were to do this using some laws of physics, that would take you a lot of time, and maybe you will never get to this equation. But anyways, what about this K? Remember we said that we didn't account for the geometrical shape of the object with the given area. Well, the geometrical shape becomes part of this K.